Hi, I'm Gordon Bell, here again at the Computer Museum in Boston. In part one of this series, we looked at the pre-war machines that led to the modern stored program computer. Now in part two, we'll look at a remarkable 10-year period. It started with one-of-a-kind laboratory computers. It ended in the birth of a computer industry. Presbert Eckert and John Mauchly met at the Moore School of Electrical Engineering in Philadelphia, and there collaborated on the design and construction of a large-scale digital computing machine. That machine was the Electronic Numerical Integrator and Computer, ENIAC, and it changed the history of the world as far as computing is concerned. The story begins with Presbert Eckert recalling those days.
Anything you can do in software, you can also do in hardware, or you can do in some intermediate ground called firmware, or by micro steps, or by whatever. It's a problem of the designer to find out what blend of those things gives the best overall mix. We had a terrible problem of the same type here, which is what caused me to think of the internal programming idea. I thought of this idea and proposed it long before von Neumann saw the stuff, by the way. The reason I thought of this is that I said, well, if we ever build another one of these machines, and when we don't just have the ballistics problems and the internal ballistics problem and a few specialized problems that we knew about to do, how do we decide how many plugs to put over here for programming, how many counters or flip-flops or something to put in the memory, how many switches to put over here with resistors, because that's going to be different for each class of problems. There are some narrow classes where it's pretty much the same, and those are the ones we were catering to in this machine. But how do I do it when the problems are wildly different? Well, I said, I've got to find a way of generalizing this. I said, everything in science that ever amounted to anything was because somebody figured out a way of taking some specific problem and generalizing it. So that what I said was that we need a memory device that's cheap enough that we can use the memory device for everything, at least at one speed level. We may need punch cards or tapes or something at some other speed level, but at least at the main speed level of the machine, we need a memory device which can hold instructions, which can hold constants, which can hold variables, which can hold information on what has to happen next, and so on. I wrote a memo saying how we could put these information all on these all in spinning disks with magnetic edges. Then I decided spinning disks with magnetic edges are really too slow to match the speed of electronics. And I had invented for a radar purpose, for some other purpose, a mercury tank device, which I, for timing purposes and for some other purposes in radar, an acoustic device in which you can store information for a limited period of time, but it dies out after a millisecond or whatever the length of the tank determines. And I thought of repeating that. The reason the size of the machine grew is originally it was supposed to be a numerical integrator to solve just ballistic trajectory, nothing else. And Colonel Gillen, who was the contracting officer in the Pentagon, in his wisdom when he named this thing, called it an electronic numerical integrator and computer. And he said he put the word and computer in there because he knew we would want to make extensions to this, and he didn't want the General Accounting Office to say, why did you allow extensions on this thing? So if you put it in the name that it's going to include more than the base thing to start with, you avoid that problem politically, if you understand. And so in his wisdom, he did that. And it turned out that it happened this way. The ballistics laboratory said, we're not only interested in what happens to a shell after it's come out of the big rifle or gun, but we want to know how it's doing as it's traveling down the barrel, which is called the internal ballistics problem. And we have some Monte Carlo problems involved in our work, and we have some other problems that we want to look at. So some of those we were able to do, and some of those we couldn't do. But we tried to amend the machine in such a way as to take on these additional requests for ability as time went on. This panel looks pretty much as I remembered, except these lights that were added since I last saw it. I don't know what they're for. But just normally to start the machine, one pressed this button here, and that turned on the heaters of the machine. And it also turned on the DC voltages. Now, we could also turn the DC voltages off and have only the heaters on, which we frequently did during testing, because turning the heaters off and on due to thermal expansion in the tubes frequently blew a tube. In fact, if you turned the machine off and on once, you could almost count on it having one blown tube, where otherwise the machine would go for 1 or 2 days at a time without a blown tube. This button over here is the initiating switch. This is the button that gave you the first pulse that started the program into operation. Now, normally we didn't do it by pressing this button. There was a button on a cord, a portable button, that could be plugged into one of the trays that carried wires around the machine. And you could actually work this initiation from anywhere around the machine. And that's because lots of times you're over testing a particular panel. You didn't want to have to run halfway across the room, which was 50 feet long, and press this. So you'd just plug this thing in where you were and press it there to start the machine again. We designed this circuit first before anything else. We tried 6 different circuits out and finally modified one of them and picked this one as the best one we could find. It had far more ability to count accurately and withstand changes in voltage and part values than any other circuit we could find. We nevertheless found it was critical of the shape of pulses that were fed into it, and so we designed a special circuit called the pulse shaper, which was found in these next 3 tubes here. Now, going to the other end, there are 6 tubes down here which comprise a transmitting device for plus numbers and a transmitting device for negative numbers, which are controlled by this counter. There are a number of tubes, as you see, intervening here. We have, I think there are 28 tubes, and we've only accounted for 13 and 6, or 19 of them. The rest of these tubes in here are primarily concerned with carryover mechanism. In other words, with remembering when 2 numbers add up to more than 9, and we have to carry it over and put it into the next channel, and to do this in such a way that the process isn't slowed down.
The ENIAC project concluded with the design and eventual construction of EDVAC. The draft EDVAC report by John von Neumann is the seminal description of the first stored program computer. In 1946, Penn held a summer school about EDVAC. It was attended by many who would build computers. This story is about 3 of the branches forming the stored program computers that came from the ENIAC project. The first branch is Cambridge University's EDSAC. Morris Wilks created the world's first operational computer. It helped stimulate the formation of a British computing industry. The second branch is the Institute for Advanced Studies Architecture Computers. A dozen or so machines were made at various laboratories using their basic design. Others, including IBM, built variants. The final branch is the Eckert-Mauchly Computer Corporation that ended up as the Remington Rand UNIVAC division of Sperry Rand. It produced UNIVAC-1, the first successful U.S. commercial computer. To be sure, ENIAC influenced other efforts, but this is about the direct descendants. Arthur Burks, who worked on ENIAC, narrates a film compiled from clippings left over from a newscast.
Press Eckert is on the left and John Mauchly on the right. Kay McNulty has just brought them a paper. I'm on the left and Herman Goldstein is on the right, in front of the 3 racks of the high-speed multiplier. From the top down, you see wiring, the digit trunk, the control panels, and the program trunk. The diagonal lines are the outputs of the shifter circuits. For each successive digit of the multiplier, the partial products were shifted one more position to the left. After the program was worked out on paper, it took a couple of days to set up the machine. Wherever possible, we mounted circuits on removable modules we called plug-in units. Homer Spence has removed a defective plug-in unit. He replaces it with one known to work correctly. Goldstein is reading numbers and Spence is setting them on the switches. This is where the resistance table for a shell was stored. That table gave the resistance of the air to the shell as a function of the shell's velocity. A problem was started at the initiating unit, but most of the equipment on this unit was for testing. These meters are for reading any of the approximately 70 direct current voltages. Here are some display lights which are operated by the vacuum tubes below. The display panel was made for this film, since little neon lights on the machine itself were not bright enough to be photographed. These lights seemed important to the film crew. They felt the public could understand visual communication between man and machine better than communication by punched cards. All electronic counters had small neon bulbs to show their state, and the same was true of flip-flops. This display board shows how an accumulator's lights might look during addition or subtraction. When the ENIAC computed a trajectory, one could see the abscissa value gradually increase as the shell traveled out, and the ordinate value go up and then come back down as the shell rose and then fell. In the public demonstration of the ENIAC, we computed the trajectory of a shell that took 30 seconds to reach its target. A young woman with a mechanical desk calculator spent 1 or 2 days calculating such a trajectory. The ENIAC computed the trajectory in only 20 seconds, faster than the shell itself traveled. This convinced the colonels and generals present that electronic computers were important.
ENIAC was moved from Penn to Aberdeen's Ballistic Research Laboratory and operated until 1955. Clearly, ENIAC was an amazing engineering accomplishment. It was dramatically larger than any other system using vacuum tubes. This rack was one of 40 panels. ENIAC was designed and built by a dozen engineers working 2 years. This figure gives the memory size plotted against operation rate for these machines. Wilkes stated, when the design work of ENIAC was finished and the construction was in progress, Eckert and Mauchly had much time to think about future developments. It did not take them long to realize that the potential existed for building much more powerful electronic computers that would also be much smaller in scale. Their thinking was advanced when John von Neumann, acting as a consultant to BRL, began to pay visits to the group. So now we begin the story of where the stored program computer we know and love got invented. The ENIAC team, as well as other machine builders, recognized that the time-consuming process of setting up problems to control computation had to be solved. It's what we now call programming. ENIAC was more general than a numerical integrator. Its function tables could store instructions and emit control pulses to the function units. It had conditional branching. Subsequently, a special function table memory was built that could also take in instructions from punched cards. In September 1944, John von Neumann of the Institute for Advanced Studies at Princeton was appointed consultant to the ENIAC project. He had learned about the control problem a year earlier in England. One task he took on was to select a permanent code for the function tables. This became known as the von Neumann code for the ENIAC. However, Eckert made it very clear that the name was not chosen because von Neumann discovered the stored program concept, but only because he had selected the instructions. A second but related problem with the early calculators was that the instructions were held by paper tape, punch cards, and plug boards. Recall both Aiken and Zeus controlled their calculators with these tapes. These slow devices were a poor match for electronic speeds. At a 1948 conference, Mauchly commented that calculations can be performed at high speed only if instructions are supplied at high speed. Eckert and Mauchly's new machine was called EDVAC, standing for Electronic Discrete Variable Automatic Computer. It was to have an electronic memory that could keep up with the arithmetic circuits and solve the control problem. It had only 4,000 vacuum tubes and a 44-bit word length. EDVAC was built at Penn and moved to Aberdeen's BRL in 1950, but the physical machine is incidental to computing. John von Neumann published the first draft of a report on the EDVAC on June 30th, 1945. This report outlined the computer architecture that remained pretty constant for the next 50 years. Von Neumann's EDVAC report describes 5 elements of a stored program computer: central arithmetic, CA, central control, CC, memory M, input I, and output O. Interestingly, the report used human analogs like neuron and memory to describe parts and processes. The central idea of the report was to use a single high-speed memory to hold both numbers and instructions. Wilkes' reading of the evidence was that Eckert had arrived at this idea before von Neumann visited the group. Von Neumann's name gave the clear credibility to crystallize, carry, and perhaps implicitly claim the concept. Wilkes further states that Eckert began his conviction that the ENIAC was more complicated than it needed to be, and that it could have been simplified by more rationalization of function. In particular, he identifies 3 quite different kinds of memory: flip-flops in accumulators, function tables or read-only memory, and interconnecting cables with their associated switches used for setting up the program. In September 1945, Eckert and Mauchly proposed EDVAC based on the stored program concept. Their report stated that an important feature of this device was that operating instructions and function tables would be stored exactly in the same sort of memory device as that used for numbers. At the 1976 International Research Conference on the History of Computing held in Los Alamos, Mauchly wrote, "Eckert and I were planning on stored programs long before von Neumann had heard of the EDVAC project." Here's Mauchly at Los Alamos describing their effort.
The ENIAC was the only existing electronic, fast, large digital computer. Why, It was not just that it had an advantage over things, it had practically an incomparable advantage, because of how else would you get many of these problems done? And so it was quite a shock to me the other night in New York to hear Dick Clevenger talk about what a terrible experience they had after the machine had been moved to Aberdeen. And the downtime was, well over 50%. Each morning when we came in and turned the machine on, a lot of things went wrong. We had long before decided, from our own experience in the Moore School, that you shouldn't turn it off and then turn it on. You should keep the filaments, at any rate, the heaters in those tubes, all of that, constantly burning, and not go through that disastrous heating cooling cycle, which not only might burn out cathodes, heaters, but might interfere and destroy with insulation and cathode sleeves and other things, any one of which would cause bad problems. And by the way we were doing these things, we would use less tubes if we used a decimal system than if we used a binary system. Was that the reason we used the decimal system? No, it wasn't. That was just a secondary reason. The primary reason was we knew that the world wasn't ready for the binary system yet. It wasn't that we were ignorant of the binary system, because we knew the whole machine was binary anyway inside. It's just, where do you convert? And so the indicator lamps and things that the operator saw were decimal. One of the whys was, why did we program it the way we did? It's a pretty stupid way, you know, to have to run around and plug wires in, have to turn switches, and so on, to convey the instructions of a problem to that computer. Well, depends on how cheap storage is. And of course we realized that storage comes at different prices for different things. If you want it fast, it was more expensive. If you want it slow, you can have lots of it. And so some people ask, well, what was the long-term storage? You know, how big was it? The long-term storage, of course, was infinite. If you punch out cards, why, nobody cared except somebody who was paying for the warehouse. But back to the ENIAC, I want to say a little more about that programming. I say that stored program would be nice. We thought so all along. Stored program wasn't in our vocabulary. Nobody had heard the word. But for that matter, nobody had heard the word of a Neumann machine then either. And nobody had heard the word EDVAC up to a certain time. So for simplicity, we did it with these plug boards and switches and things. That simplicity, of course, bought us time. We were really trying to finish that machine before the war was over, because we didn't know when the war would really be resolved. And here we were in '43, trying our best to get that machine going and useful. That old monster, ENIAC, had a stored program, if you wish to call it that. If you can reorient your thinking and your translation of language, what we call a master programmer was essential to putting any program that was putting on any problem that was worth putting on an electronic computer.
Much attention could be paid to Penn's efforts once the project was declassified. Researchers from around the world came to visit. In the summer of 1946, the Moore School offered a series of summer lectures to gather everyone interested in computing. Wilkes and Sir Frederick Williams came from England. Howard Aiken came from Harvard to speak. But the focus was plans for the EDVAC. Williams and Tom Kilburn had the first operational stored program computer at the University of Manchester. With only 32 words of 31 bits, it was only built to test the electrostatic Williams tube memory for their Mark I. However, it ran a 17-word program for 52 minutes on June 21, 1948. In February 1951, their Mark I, designed along the lines of the IAS parallel architecture, was introduced as a product by the Ferranti Corporation. But that's another story. Morris Wilks returned to Cambridge with the burning desire to build an EDVAC-like machine. The project got started in October 1946. EDSAC became the first full-scale stored program computer to operate. It first ran on May 6, 1949. EDVAC instructions had 4 addresses stored in a 44-bit word. Thus, an instruction could point to the optimum memory locations. EDSAC instructions had 1 address and were stored in a 17-bit word. So EDSAC traded off potential performance for a memory efficiency. Wilks' EDSAC movie, shown at the 1951 Joint Computer Conference in Philadelphia, provides us with a great view of what computing was like at that time.
The mathematician explains his problem to a committee of experts. The first thing to do is to make a list of the library subroutines that will be needed. A subroutine for quadrature, one for the exponential function. A member of the committee interrupts to point out that there is a more suitable exponential routine available. A read routine and a print routine. The committee proceeds to discuss the programming of the problem. The programmer gets to work referring to the library catalogue as required. Here is the program sheet. The program is now checked and it is ready for punching. This is Margaret Hartree, who was my secretary at the time. She is in the course of punching the tape, and at the appropriate moment she will go over to get one of the library tapes. This she copies mechanically onto the tape that she is preparing. The recommended practice, not always followed, was for a program tape to be punched twice and the resulting tapes to be compared mechanically. She finishes off the tape and takes it over to a comparator to compare it with the other tape. As long as the 2 tapes are identical, the comparator runs, but if there were a discrepancy, it would stop. She takes the tape to the computer room, attaches a tape ticket, and puts it on the job queue. Meanwhile, the EDSAC is running on some other problem, and the operator is waiting for the results to come out. Output was not quite as voluminous in those days as it is now. She puts it in the rack, takes our program tape, and puts it in the photoelectric tape reader. The instructions are being read and going into the store. The next tank. Now numbers are being read, and here you see the numbers in the store changing as the calculation proceeds. These are all short numbers occupying half a word. While the program is running, we are shown some shots of the EDSAC. The storage tanks are in a thermostatically controlled oven. Panels showing some of the vacuum tubes. Back of panel wiring. A shot from above. The results are now coming out. This is one of the other programmers coming in for her results, but she must have made a mistake. We used to use for debugging a trace routine that would print the function letter of each instruction as it was executed. Our programmer collects his results. He is joined by the mathematician, and apparently all is well.
EDSAC's notoriety attracted attention with the possibilities of commercialization. The president of the Lyons Company, a tea shop concern in England, realized that a computer could be a valuable tool for his business. Lyons formed a division to commercialize EDSAC. Here's a film about their machine, Leo.
Despite the large numbers of clerks employed today, sufficient clerks are still hard to find. With full employment, the security of clerical work does not offer the old attraction. But trade is becoming more competitive, so clerks are in even greater demand to provide statistics from a mass of data so that management can grasp the changing factors and act accordingly. To fulfill this modern need came Leo, the first automatic office in the world. Electronic computers are not new, but Leo was the first designed for office work. Since 1953, it has been employed regularly on accounting, stock and cost control, statistics, and, of course, payroll. Leo is fast and flexible. It can test the feasibility of the information that is fed into it and check the accuracy of its own results following orthodox accounting principles. Leo can be installed anywhere. It does not require air conditioning, having its own ventilation system. It is supplied complete with equipment for stabilizing the mains voltage. Leo Mark II has 4 channels for input of information and 4 more for output. This particular installation is using 3 input channels, 2 coupled to punch card readers and 1 to a punched tape reader. Its output can be routed to card punches for machine reading or any of the normal printing devices. Any other suitable form of input or output can be coupled. Leo is set in operation from a console. It is here that its performance can be monitored. J. Lyons, besides payroll, require their Leo to do several other routine clerical jobs. A job done every afternoon concerns deliveries to their 150 tea shops in London. There are hundreds of items of food. Bakery goods of all kinds, kitchen goods in a wide variety, for the breakfast, lunch, tea and supper trade, and for take-home sales. All these, in a varying quantity each day, are delivered to a precise timetable to the tea shops. Understocking leads to lost sales, but with food, overstocking soon becomes intolerably wasteful. Each manageress has a standing order depending on the day of the week. After lunch each day, she considers her stock, weighs up local conditions, and decides what variations, up or down, she will make to her order. She speaks by telephone to head office, where her variations are taken down directly onto cards. There is no written record. What the girl hears, she punches. At the same time, a short paper tape puts in last-minute management decisions, such as occur with changes in the weather. Thus is flexibility provided. Again, the program is fed first, laying down the sequence for the multiplicity of calculations Leo will perform. Next, the standing orders and the telephoned revisions, T-shop by T-shop, are fed in, with the overriding variations on the paper tape. Immediately, packing notes begin to print out, 10 shops at a time. At the same time, charges to T-shops and sales statistics are being recorded. After further electronic processing, these cards provide the statistics for the use of the management. By means of discriminants built into the program, Leo will examine all statistics, but only print the ones that require action. Managers are, in this way, given precise, up-to-the-minute information, enabling decisions to be more closely related to trading conditions. The packing notes, which were printed by Leo 10 to a sheet, are separated, guillotined, clipped to a packer's board, and sent to the dispatch. Subtotals of the different items have been worked out for bulk movement to the several loading bays. Although the last revision is not telephoned until 3:30, by 4:30, Leo has printed for 150 tea-shops and 40,000 items exactly what is wanted at each tea-shop, in the right order for the different loading bays. They are also in the right order for the carman's calls, so that the goods at the front of the lorry can be delivered last, and the first call is just inside the doors. These are only a few examples of the wide range of work undertaken by Leo. Building each automatic office is the result of skilled investigation and design. Each application, similarly, calls for the experience and know-how of using automatic offices. Leo Computers Limited undertake all this in conjunction with the user's staff. Leo is a machine that does routine clerical work more quickly and more accurately than clerks. The clerks are freed for more rewarding and productive work as the use of Leo expands.
Let's now go to the Institute for Advanced Studies at Princeton and the IAS parallel machines. The design was described in a series of papers by Arthur Burks, Lieutenant Herman Goldstein, and John von Neumann. A paper called The Preliminary Discussion of the Logical Design of an Electronic Computing Instrument was published June 28, 1946, exactly 1 year after the draft EDVAC report. Brian Randall points out that although the IAS computer was not finished until 1952, the series of reports that were issued by the project were widely circulated and served many people as textbooks on logical design and programming. The plan was to use an electrostatic storage tube as an alternative to mercury delay lines. This provided random access rather than cyclic access, with each word being read in parallel rather than serially. As a result of the papers, many parallel binary machines, or von Neumann machines as they came to be known, were started up. One such project resulted in the IBM 701, forerunner of a whole series of machines which within a few years became the dominant large-scale scientific computers. The IAS design specified a 40-bit word that held 2 instructions. The memory was held in a bank of 40 cathode ray tubes. 12 bits were used to address memory, and 6 bits specified the operation code. Their design uses a function table register FR to address instructions, retaining the ENIAC nomenclature. Thus, the parallel IES machine, the EDVAC report describing the stored program concept, and the von Neumann computer all became synonymous. Parallelism gave the IES more than a factor of 40 in performance over the EDVAC. Altogether, the IES had about a dozen direct descendants. The first to operate was Argonne's Avidac in 1951. Oak Ridge had them build a copy called Oracle. The University of Illinois built Ordvac for BRL and a modified version, Iliac, for themselves. Ciliac, Cyrac, Wizac, Cyclone, Mystic, and computers at Iowa State and Michigan State were created in Iliac's image. Here's Johnniac. It was built by the RAND Corporation to test transistor logic. It also acquired a core memory which was placed at the top of the machine. Maniac, the Los Alamos version of the IAS, became operational in early 1952. Our next film is an excellent description of the IAS computers. Even 50 years later, it is a wonderful introduction to the 5 classical boxes often used to define a computer.
The fundamental operation of the Maniac is illustrated by a block diagram of its basic components. A problem is fed into the input section, a little at a time. As soon as the input is loaded to capacity, the control is notified and responds by sending back to the input an order to deposit its contents in the memory, making room for more of the problem in the input. This goes on rapidly until all of the problem is in the memory. The solution of the problem then begins. A button is pushed and the control tells the memory to send some material down into the arithmetic unit so it can be worked on. When an operation is completed, the arithmetic unit notifies the control. Intermediate and final answers are stored in the memory. Finally, the control instructs the memory to deliver the answer to the output and orders the output to phrase the answer in usable form. The Maniac can be useful only when it is told precisely what to do in a language it understands. A problem submitted to it for solution must contain 2 kinds of information: the actual numerical quantities involved and directions indicating exactly how they are to be handled. This material is logically interwoven in a preliminary coding process where it becomes a collection of symbols depicting the operations in the computer required to accomplish the solution of the problem. The coder works from a flow diagram which has been drawn up by the author of the problem. This diagram is essentially a picture of the path to be followed by the computer in the solution of the problem. The diagram consists of directional flow lines broken at appropriate points for the insertion of boxes indicating the computation to be performed locally. Represented here are various necessary logical steps and decisions, as well as purely mathematical operations. Also, memory information where necessary. A problem in its final coded form is a sequence of instructions. Each instruction is made up of an order and an address. An order is a command to the machine to perform a specific operation. In code, it is a combination of 2 letters in the range A through F. There are about 30 such combinations in use. Problems of commonly used types are accumulated in a tape library. The use of the basic portions of these problems in the taping of similar problems results in a considerable saving of time. A taped problem enters the computer through a photoelectric reader which feeds in words at the rate of about 20 per second. The end of the tape is placed in the reader, the load switch is flipped, and the problem goes into the machine. An average problem is loaded in perhaps 15 seconds. In the reader, the problem becomes the series of electrical signals with which the computer does its work. The signals are sent first into one of the 6 registers of the arithmetic unit. A register consists externally of a horizontal row of 40 neon lamps set in a narrow strip of black bakelite. Vertical white stripes divide the main registers into groups of 4 lamps, representing tetrads. Each lamp is connected with an electronic flip-flop circuit. Each register thus contains 40 flip-flops. A lighted lamp results from a hole in the tape and means a binary 1. No light is a blank or a binary 0. Thus, a register may be regarded as an indicator of events occurring in the arithmetic unit. The problem is next transferred from the register to the memory. The MANIAC's principal memory is of the electrostatic type, utilizing 40 standard 2-inch cathode ray tubes, mounted in individual metal cases above the arithmetic unit, 20 at the front and 20 at the rear. A tape can be designed to write almost anything in the memory. The register and memory are connected in a so-called parallel fashion. One flip-flop of the register communicates through an electronic gate with one and only one storage tube in the memory. For convenience, all material of a particular type used in the computer is stored in its own arbitrary block of addresses in the memory. The blocks are filled with words in a definite sequence, from top to bottom and from right to left. A spot in any tube is the residence of one of the 40 binary characters of a word. All characters of the same word reside at the same address in their respective tubes. The memory, when completely filled, contains a total of 1,024 times 40, or 40,960 binary characters. The array is about 1.5 inches square. These spots on the tube faces are being regenerated continuously. If they were not, they would fade away in a short time, and important information would be lost. An auxiliary storage device, a rotating magnetic drum with 200 heads, increases the memory capacity of the machine by a factor of 10. Words are handled in blocks of 50. The relatively slow operation of this system makes it useful only as a supplementary memory. To prevent excessive loss of time and information in case of power or component failure, blocks of material are brought out from the memory and put on magnetic tape to be referred to if necessary. This feature is especially useful in the case of unusually long problems requiring several hours of computation. A problem may reside in the memory indefinitely, but it can't be solved there. The instructions of which it is composed must be withdrawn in proper sequence, interpreted, and carried out. The solution of a problem starts when a button on the operating desk is pushed. Instructions are transferred from the memory to the top or control register of the arithmetic unit. Orders and addresses are separated in a set of function circuits, and orders are sent to a diode matrix for interpretation, while addresses go to the memory control circuits for consultation of the specified spots in the array. The matrix is a sorting device. Each of the 30-odd orders which might enter it is recognized and sent to an electronic programmer which arranges for the execution of the order. The active elements of the matrix are crystal diodes which are mounted in sets of 6 on octo plugs. The memory circuits act to question the address involved in the instruction to determine what information it contains. This information is sent to join the order information in the programmer. The required operation is then performed, and thus an instruction is carried out.
In March of 1946, Presper Eckert and John Mauchly left the Moore School. They formed Eckert-Mauchly Computer Company in December 1948. Their first product, BINAC, was shipped to Northrop for onboard missile control in August 1949. BINAC was really a circuit prototype for the ambitious UNIVAC 1 that was accepted by the U.S. Census Bureau in March 1951. UNIVAC 1 used a delay line memory to store 1,000 12-digit words. Each word held 2 6-digit single address instructions. It was decimal, like ENIAC, and was designed for data processing. UNIVAC had extensive checking circuitry and a complete I/O system including tape, printers, and offline data conversion. In order to deliver their million-dollar machines, Eckert and Mauchly had to get funding to survive. Remington Rand purchased them. With capitalization, about 20 UNIVACs were delivered by 1954. In 1952, Remington Rand also purchased the Engineering Research Associates making scientific drum computers. These evolved to the 1103 that competed with IBM 701. Both used a 36-bit word and parallel architecture like the IAS design. This November 1952 newscast shows the UNIVAC in action predicting the election. UNIVAC called for a landslide for General Eisenhower after looking at just a few returns, but its keepers wouldn't let it speak out and waited for the returns to be tabulated manually. The story I've told here covers a decade from 1943 to 1953. At first, no computers existed. 10 years later, many laboratory-built computers were in operation. Several computer companies, including IBM and UNIVAC, were designing and shipping scientific and business computers. This was the beginning of the computer industry. From the Computer Museum in Boston, I'm Gordon Bell.